the vector itself. Yeah.
Yep.
All right, so I'm going to go through a few.
Yes.
So this quickly to go through some of the questions in your midterm. So the first question is, if S is a symmetric matrix, and S is a 3 by 3 symmetric matrix, and it has 3 eigenvalues that are greater or equal to 0, is S a semi-positive definite symmetric matrix or not? So if you have provided half a proof by saying if P1 or P, Q, and R are eigenvectors, corresponding to lambda 1 and to lambda 3, then we know that P dot SP will be equal to P dot SP is equal to lambda 1 P. Lambda 1 is a number. I can take lambda 1 here. P dot P. The dot product between the vector and itself is always greater than 0. And P is not equal to 0. So this is greater than or equal to 0, and this is true for Q dot SQ and R dot SR. Now this is half a proof, because what is the definition of semi-positive definite? The definition of a semi-positive definite is that for every x in R3, x in R3, we have x dot Sx is greater than or equal to 0. Now what you proved is that for 3 particular vectors, which are P, Q, and R, the P dot Sp is greater than 0, Q dot Sq is greater than 0, and R dot Sr is greater than 0. But what you need to prove is that this statement is true for any x, because the definition says for any x. So to do this, you can more choose. There are many different proofs, but they all rely on the same concept, which is choosing a basis set P, Q, R. These are 3 perpendicular vectors. I can use these as the basis set. And now any x in R3 can be represented as alpha p, or let's say x1p plus x2q plus x3r, where x1, x2, and x3 are real numbers. Now try to take x dot Sx, and this you'll find will be equal to assuming that P and Q and R are unit vectors, P and Q and R are perpendicular to each other, you will get lambda 1 x1 squared plus lambda 2 x2 squared plus lambda 3 x3 squared, which is always greater than or equal to 0. So if you've done up to here, you got 5 out of 10. So you all did well. I mean, the average was high. So you're all going to get good marks anyway. I don't know what would be worth. Question 2. We have a function defined as follows. F of A. F takes from R3 to R3. F of A is equal to V dot A U. Is F linear? And V and U are fixed vectors. Well, we have to see the definition of linear. The definition of linear is that for every alpha and beta in R, for every x and y in R3, I have to have f alpha x plus beta y and alpha f of x plus beta f of y. These have to be equal. If these two are equal, then f is linear. If not, then f is not linear. Let's try f of alpha x plus beta y. This go instead of A. So this is v dot alpha x plus beta y in the direction of u. This is a dot product. The nice thing about the dot product is it's linear. So I can have of v dot x plus beta v dot y. This is a number and this is a number multiplied by u. This can be written like this. Which is equal actually alpha f of x plus beta f of y. So it is indeed linear. Now any linear function from R3 to R3 can be represented by a matrix. So what is the matrix that represents this particular function? We're saying f of A, which is equal to v dot A u, is equal to a matrix multiplied by A. What is this matrix? If you do it with the components, now let's do it with the components. V dot AU, V dot A is equal to V1, A1, plus V2, A2, plus V3, A3. I'm not even going to use the summation convention just to make it easy. V1, A1, plus V2, A2, plus VA3, 3A3. That's a number multiplied by a vector U1, U2, U3. Now I want A1, A2, and A3 instead of U1, U2, U3. You're going to find that this is equal to V1, U1. I'm going to multiply this by this. I will get first component here will be equal to V1, U1. And V1, U1, V2, U1, V3, U1. So U1, V, U2, V2, sorry, V1, V2, V3, V1, V2, V3, U1, U2, U3, U1, U2, 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 and U3, U3, U3. So the matrix is basically VI. So the matrix IJ is equal to which row is I, UJ. And if you do it by components, if you're easier to work with components, f of A, it's a vector that has a component I, so this is Vj, Aj, Ui, Ui, Vj, Aj. This is equal to the matrix Ij, Aj. So M Ij is equal to Ui, Vj. So, C, prove that it is a subspace. To prove that it's a subspace, what is a subspace? F of R3. So let's understand graphically what F of R3 means. What does F do? F takes any vector A, F acts on A to give me V dot A in the direction of U. So I have a vector A, I'm going to take the dot product of V with A, V is fixed, and the result is in the direction of U. So when you see this picture, what do you think the dimension of the set f of R3 equal to? What's that? Can't hear it. Well, it's a subspace. F of R3, this is F of R3. F of R3 can only be here, because you cannot get a vector, any vector here, let's say Z, it's not an image of any vector here. So what's the dimension of that set? What's the dimension of this set? Just one. So yes, F takes a vector and gives me another vector, but the set that F gives me a subset of R3. So F of R3 is a subset of R3. It's not equal to R3. It's only it gives me one. It gives me only a subspace of R3. And the dimension of that is 1. If you look at, okay, well, what is the definition of the dimension? The definition of the dimension is that it's the number of vectors in the basis set. Now, f of R3 is equal to a number multiplied by u. It's always equal to a number multiplied by u. Therefore, so f of R3 is a set that's made out of alpha u, where alpha belongs to R. Therefore, the basis set of F over R3 contains one element, U, or a multiplication of U, because any element in F over R3 has can be written as a multiple of U, because it can be written as a multiple of U. It's equal to 1. Now, I realize that these things are new to you, and that's why I didn't put a lot of weight on it. So if you didn't get it right, don't be upset. You haven't done this before. So I just want you to learn from these things, not to be upset that you didn't get it well or you didn't do well. Because I mean, this whole thing is worth 5, and the linear is worth 2. So it's not. I didn't put a lot of weight on these. But you should know, because these are basics for everything else that you do. So question 3. So for question 3, we're saying the following. I'm just going to write the statement. We have two vectors, P, Q in R3. This is P, and this is Q. And it happens to be that if for every U, R3, U dot P is equal to U dot Q. It happens that if I take the dot product of U with P, and I take the dot product with Q, I get the same number. And I'm saying that this implies P equal Q. Now, is that true or not? Well, it is true, because I'm saying show that the following statement is true. Now, the question is, a vector is well defined. If I tell you that here's a vector P, it's well defined. If I give you 3 components of P, it's well defined. Now, if I tell you nothing about those 2 vectors, except the fact that this vector, I know exactly what the number is when I take the dot product of this vector with every vector E. So basically what we're saying is, a vector defined. Can I define a vector just by knowing the result of the dot product? Because if I know the result of the dot product, that for every U, U dot P is equal to U dot Q, is this enough to tell me that P is a unique vector? Which means if I have 2 vectors that give me the same dot product with every U, does this imply that P is equal to Q or not? And it is indeed, because I can choose any, this says for any U, so I can choose any U. So let's pick U. I mean, there's many ways. The most elegant way, but it's not necessarily the best way, the most elegant way is to say U dot P minus Q is equal to 0. Pick U is equal to P minus Q. Therefore, P minus Q dot P minus Q is equal to 0. But this is only equivalent to P equal to Q. That's the properties of the dot product. You only get the dot product of the vector equal to 0 if and only if that vector is equal to 0. So this is the most elegant way to prove it. U dot P minus Q is equal to 0, because U dot P is equal to U dot Q. Therefore, U dot P minus Q is equal to 0. If you pick U, we're saying that this is true for every U. So I will pick U to be equal to P minus Q. So I get P minus Q dot P minus Q is equal to 0. But from the properties of the dot product, P minus Q dot P minus Q is 0 if and only if P is equal to Q. That's the most elegant way. Or pick, or some other people said, well, I've got U1, P1 minus Q1, plus U2, P2 minus Q2, plus U3, P3 minus Q3, equal to 0. And they wrote, since, which is true, U1, U2, U3 are arbitrary, which is true. Basically, we're saying I can pick anything for U1, U2, U3. So I can pick U1, 1, and U2 and U3, 0. Or I can pick U1, 0, U2 is 1, and U3, 0, and so on. But since they are arbitrary, you'll find P1 is equal to Q1, P2 is equal to Q2, and P3 is equal to Q3. So indeed, if I have two vectors that give me the same dot product result, when I take the dot product with any other vector, that implies right away that these two vectors are the same. So question 4. Question 4 states the following. If Tx equal lambda x, where x is a vector, T is a matrix, lambda is a real number. Does this imply T n x equal lambda n x? Is this true? Well, let's see for 2. T multiplied by Tx is equal to T multiplied by lambda x. This is a real number, so I can take it out, because this is a linear operator. So I take the number out. But T of x I know is equal to lambda x, so this is true for lambda nx. Sorry, lambda square x, and depending on how you want to do it, if you use induction, but you guys don't know induction, but if we say T n x, some other people did it like this, T, which I thought very nice, n times n minus 1 times multiplied by Tx, here n minus 1 times multiplied by lambda x, because Tx is equal to lambda x. All these are linear operators. You can take the lambda out, and so on until you get lambda n power x. Which basically means if T is a linear operator with an eigenvalue lambda, then if you take T and multiply it by T and multiply by T n times, you'll get lambda power n as an eigenvalue as well. Now, we never said that T is a symmetric matrix, and we never said that T is a diagonal matrix. So you cannot assume that T is a diagonal matrix. You cannot assume anything that is not given. T is just a general operator. And T power n, when we say T power n, we don't mean the components of T power n. We mean that you must take the whole T, let's say 3 by 3. Now this applies to any dimension, not necessarily 3 by 3. But T power n, if this is T, and I take T again, T squared is equal to, you take this multiplied by this, you get a number. This multiplied by this, you get another number. This multiplied by this, you get another number. So it's not equal to the individual components power n. It's not equal to Tij power n. That's not true. And the rest, I think everybody did really well in question 6 and question 7 and question 5. Do you guys have any questions about this? So again, if you didn't do well, it doesn't mean anything. This is just new material. Just try try to, just hopefully after the midterm you understood things a little bit more if you didn't do well in the midterm. But these things are basics for everything that we do in solid mechanics, and in fact they're basics for a lot of things that are done in engineering. And just don't be upset if you didn't do well. It doesn't matter. Just be upset if you still don't understand what's going on. Then just come and ask. All right. So for today's lecture, we are going to talk about the following. Three things we would like to talk about. The first question is, or the first thing we want to talk about, what is the elastic energy that is stored during deformation? And for this, we'll find that this elastic energy per unit, which is energy per unit volume, is equal to the integral sigma on 1 d epsilon on 1 plus sigma 2 d epsilon 2 and so on, which is equal to the summation of sigma ij d epsilon ij, which for linear elastic, if the stress is directly proportional to the strain, this is equal to sigma ij epsilon ij over 2. So this is the first thing we want to talk about. The second thing we want to talk about is that for large deformations, the energy is a function of lambda 1, lambda 2, lambda 3, where these are the principal stretches the positive square roots of the eigen values of F transpose F. So this is for large deformation isotropic materials. And the last thing that we want to talk about is virtual work. What is the virtual work? So the virtual work statement says during any deformation, the internal virtual work or the external virtual work is equal to the internal virtual work. What is the internal virtual work? This is equal to the sum of sigma ij epsilon star ij integrated over the volume. This is equal to the external virtual work. The external virtual work is equal to the work done by the external forces on the surface plus the work done by the body forces inside the body. So we want to prove this statement. Now, to cover all these things, I'm just going to start from single degrees of freedom, just to remind you of what these concepts mean. For a single degree of freedom, I'm going to talk about what is energy, what is the energy of deformation, what's all these things. So I'm going to start with a single degree of freedom system. Single degree of freedom system made out of a mass, mg, that's acting downwards, and let's say x is positive downwards, and a force, a spring force that's equal to function of x, and this function is linear. Every time I extend this spring with a distance x, I get a linear force, or a force that's function of this x as a linear function that's equal to k multiplied by x, where k is the slope of that relationship. Now, in general, kx is not equal to mg, because I can have large x, small x, but at equilibrium, k multiplied by x at equilibrium equals to mg. So let's call k at equilibrium delta. So k delta is equal to mg. Now I'm going to integrate this thing. I'm going to define kx minus mg. I'm going to integrate this with respect to x. And I'm going to call this the potential energy of the system. It's a force multiplied by the distance. So it's an energy. So I'm going to integrate this with respect to x. What do you get? Kx squared over 2 from 0 to x minus mgx. Now this is just a quantity function of x. Now, looking at this quantity, I have two things. This is what I call the energy stored in the spring minus the work done by external forces. The work done by mg when I move x is mgx. And the energy stored in the spring is equal to kx squared over 2. Basically, for any x, this energy is equal to kx squared over 2. Because at equilibrium, kx or k delta is equal to mg, which means that at equilibrium, we have partial potential energy, like partial x, is equal to kx minus mg. When you substitute delta here, you get a 0. So what does this mean? It means at equilibrium, it means one of the following. This is x and this is the potential energy, and this is delta, it means one of the following. Either the potential energy looks like this, or looks like this, or looks like this, or even constant. One of these. How do we know which one? We take the second derivative. second derivative of the potential energy with respect to x squared is equal to k. The slope of the stress strain curve, or the force displacement curve. Now this is greater than 0. Therefore, potential energy x, this is delta, k is greater than 0, that means the potential energy of the system looks like this. At equilibrium, it is minimum. Now this concept applies that the potential energy is minimum at equilibrium, whether the force displacement curve of the spring is linear or if it's nonlinear. But there's a slight difference. Difference between curves on A and B and curves on C and D. What's the difference between the curves A and B? So let's just write the same equations. Now I have f of x, which is a nonlinear function, minus mg is not necessarily equal to 0, but at equilibrium, f of delta equilibrium is equal to mg. Now I'm going to define the energy of the spring as the integral of this function. I'm going to define the potential energy of the system as the integral of f of x dx minus mgx, which is equal to pi spring minus mgx again. The second derivative, the first derivative of potential energy with respect to x will give me f of x minus mg, which is equal to 0 at equilibrium. So again, the same picture applies. The same picture applies. The potential energy is either minimum constant or maximum. So how do we know? We have to calculate the second derivative of the potential energy with respect to x squared. The second derivative of potential energy is equal to the slope of this f of x. So whether the system is in equilibrium or not depends on the slope. Whether the system has a stable equilibrium or not depends on the slope of the spring force. If the slope is positive, then I get what we call stable equilibrium. So for whether I'm talking about A or B, you get a stable equilibrium. Once you go into something like C or D, when the slope of the stress strain or the force displacement curve is moving downward, and when you have a negative slope, this is the potential energy of the system is actually maximum, not minimum. Potential energy of the system is maximum, not minimum. That means that the system is really unstable. It's just waiting for any perturbation to move away from equilibrium. And let's look at it. Let's pick any point. Let's pick point x1. Let's say that the external force F is in equilibrium with x1. So now I have f of x1 in equilibrium with the external force F. And let's say the wind comes and pushes F in this direction a very small, or pushes this point in this direction a very small distance. So as it moves in this direction, the force in the spring actually decreases because we have a stress or force displacement curve that's decreasing. As the force decreases, but we know that the capital F is now greater than F of x2, which will make that force even go further. And so this is an unstable equilibrium, and if any perturbation at this point, the spring will extend really fast in one direction or the other. Now this is, and this is the difference between what we call load control and displacement control for the stability of the system. This system, let's look at the system. Let's just, oh, there it is. This system, so A and B are both stable under whether you apply displacement or load control. Whether you apply force or displacement, you're going to achieve equilibrium or static equilibrium when the external force is equal to the internal force in the spring. Now this system is only stable under displacement control, because if you apply displacement, you get a force, that's it. And you hold that spring at this particular displacement, you get a force. But if you try to achieve equilibrium using a force, you will not be able to achieve equilibrium for a particular force, because if you're here and you try to apply a certain, or if you try to apply a high force, then you will not be able to achieve equilibrium. Everything that is here, everything that we talked about, applies to whatever constitutive law I need for the material. Because looking at, this is analogous to an object that's deforming. K is analogous to the stiffness of the material. If I have a material that I'm deforming, K is equivalent to the stiffness of that material. And so the requirements for stability is that K has to be greater than 0, and K is greater than 0, or the slope of the force versus displacement has to be greater than 0. For the constitutive law of the material, that also implies for the material to be stable under loading, that also implies that the stiffness of that material has to be positive definite, or has to be greater than 0. This is just a numerical example. Actually, I use this for the undergrad. Just a numerical example. If you have a force versus displacement, just identify the points where the slope is 0, and that's where that whatever spring you're using is unstable. So, this is just some facts from mathematics. A continuously smooth function, f of x, pi, the second pi spring, this is the potential energy of the spring, whose second derivative is always higher than 0, second derivative is always higher than 0, belongs to something called the family of convex functions. And if pi spring, instead of pi spring, is analogous to the internal energy in a continuum, then we would like that whatever internal energy that we define has to be convex in its values. And we will talk about what forms of the internal energy we can have. Now, in the next lecture, if we finish what we want to finish today, maybe next lecture, at the end of next lecture, we're going to start introducing what we call plasticity, or plastic materials. So what's the difference between what we talked about now and plastic materials? The difference is that I don't have an elastic, this pi spring does not so pi spring is not equal to f of x dx. Because if you load and you unload, you don't follow the same path. So this energy, the energy during loading and unloading is not equal to the area under the curve. As I load and unload, I follow a different path. And that path depends on where the point of unloading and depends on the material. So what happens here? Well, what happens here is that I have some energy that is lost. Where is this energy lost? It's lost in many forms. It could be lost as heat. It could be lost, and usually that also implies that there is some sort of internal change of the structure, implying damage. So, for example, for this particular case, as I load and then unload, the spring, there is some change in the internal structure, and the spring does not go back to its original position. There's some sort of, from a structural point of view, there's usually some damage inside that spring, because next time I load it, I have a different behavior, and if I keep loading and unloading, I will, without actually reaching the ultimate tensile or maximum stress that this material takes, if I just keep loading and unloading and keep damaging the material, sooner or later it will just snap without reaching the maximum stress. Unless it reaches maybe I'm loading and unloading in an elastic manner, but usually as long as there's some dissipation of energy inside the object, then I'm causing some damage that will eventually lead to this spring breaking. Now, we're not going to do any dynamics in this course, but I would like to just talk about it briefly. What is the difference between, because a lot of you might end up doing some dynamic analysis or use some finite element analysis software to do dynamic analysis. So what is the difference between what we talked about and dynamic analysis? The difference between static and dynamic is the following fact. In static analysis, we're saying Kx is not necessarily equal to mg, but in static, but what is x so that Kx equal mg? So what is x? What is the deformation of the object so that the external forces are in equilibrium with the internal forces of the object? And in doing so, you can say, well, minimize the potential energy. To find x. And this is what we do in finite element analysis, for example. Or in the Rayleigh-Ritz method, which we talked about. Minimize the potential energy to find that x, to find x at equilibrium. Now, and then that's why not every static analysis will have a solution, because you might apply a force that the structure cannot take, or you might apply a force that's changing so much, changing really fast with the application of the load. With the displacement, you can apply a force that changes with the load such that you can never reach static equilibrium. And that's why not every finite element analysis, not every static finite element analysis has a solution. Because maybe static equilibrium does not exist. Dynamic equilibrium, on the other hand, is a different situation. There's always dynamic equilibrium. As long as I know what the actual external forces are, then the dynamic equilibrium states that mg, the external forces minus the resistance of the structure is equal to mx dot dot dot. That's true for every x, for every time, and for every velocity. At every point in that structure, I have mg minus kx is equal to mx dot dot dot. And that's why, because this is true for every x, for every t, for every x dot, just give me the initial condition, put it in a finite element analysis, and apply small time perturbations. As I have the external forces, I know the acceleration of the structure. After 1 second, I know where the structure has moved. And so in finite element analysis model, for example, when you do this, how does it do it? Let's say you have a few elements, and you're doing a dynamic analysis where you're applying a force here. I know this force, I know the mass of this element, I know the acceleration of this face, I know the acceleration of this face in a time t equals 0.1 seconds, for example. I know where it has moved. So you can see a wave. The first element extends. T is equal to 0.2 seconds. Then you get this face is now here. Now the next element has even extended. And the elements in the back has not felt anything yet. As time progresses, you see the movement of the structure. So in a dynamic equilibrium, this is in a dynamic equilibrium because this equation always holds. And because this equation always holds, when you integrate this, you get what we call the energy. And for this case, the energy is constant. Why is it constant? Because the derivatives is equal to 0 for every x, for every t, for every x prime. So the difference between this case and this case, here the potential energy was minimum at equilibrium, but for the total energy is constant in a dynamic equilibrium. And this total energy for a structural system, when you integrate this, mg minus kx equal to mx dot dot, let's do that integration. You can integrate it. So I'm going to integrate it with respect to the x, but dx is equal to the velocity dt. So x dot dt minus mg x dot dt plus mx dot x dot dt. This is always equal to constant, and you'll get again half kx squared minus mgx plus mx dot squared over 2. And this is the total energy of the system, and the total energy, you will see, is equal to potential energy of the spring work done by external forces this is potential energy of system, and this is kinetic energy. And so you have this equilibrium between the kinetic energy and the potential energy of the system, because the sum is always equal to constant, because the dynamic equilibrium is applied and is equal at any velocity and at any point in time. and you get the potential energy is equal to the sum of the potential energy, and the kinetic energy is always equal to a constant. Now, have you guys designed any, or have you taken any structural analysis course where you're designing the structure under dynamic analysis? Have you ever heard of a dynamic factor? What is the dynamic factor? What's the maximum factor that you can use for dynamic analysis? Do you know? Is it 3? Is it 2? Is it 1.5? So if somebody comes and says, the dynamic factor that I use for this structure is 3, would you say anything? Sure? Any opinions?
Doesn't it depend on many things?
Okay, well, sure, it depends on the initial conditions, but you can say it depends on many things. But for bridges in particular, okay, well, let's ask this. If the bridge is short and if the bridge is long, okay, let's compare these two things. If I have a short bridge and I have a long bridge, and the cars, this is the ground, this is the ground, and the cars, yeah, I miss those days when I was high. Horrible at drawing. So, which one would have a higher dynamic factor when you design? The longer bridge or the shorter bridge? Does everybody agree? Yes or no? No? Who agrees that it's shorter? Okay, who agrees it's longer? So, indeed, the shorter bridge has a higher dynamic factor. When you design it, the shorter has a higher dynamic factor. And the reason is because as the car goes, assuming the car has the same speed, the car reaches the middle faster than in the larger. So this shorter bridge would actually feel the dynamic effect more because it reaches, let's say, the maximum is when the load is applied here, and the maximum is when the load is applied here. As the car, this is really applied more gradually than this one, because if it takes it 1 second to reach this F, here it's going to take it, depending of course on the speed, so you're right, depending on many factors. But this will take longer to reach the same point, so the dynamic effect on a shorter bridge is more. But when you look at the solution to the system, when you solve this equation, to find what x is, depending, of course, what you're saying is that depending on many things, which is basically depending on the initial conditions of the system. If I start when x equals 0, so at time equals 0, x equals 0, and the velocity is equal to 0, if these are my initial conditions, and then all of a sudden I drop a weight m on this spring, if these are my initial conditions, then what will happen is this m will keep moving up and down around the equilibrium position, where this is 2 delta. Because because this is 2 delta, and if it's a linear spring, which means the force is directly proportional to the displacement, if the equilibrium position is delta, then what is the dynamic factor? So the force in the spring is actually double the static equilibrium. So in the worst case scenario, when I drop the weight fully from the initial position to 0, the maximum dynamic factor is 2. Now, if you have an initial velocity, that too might increase, but you're assuming you don't have an initial. So if you have an initial velocity, if the bridge is vibrating already, and as it's going down, you impact it, then sure, you're increasing that, the dynamic factor is higher. But if the bridge is stable, starting from a 0, and all of a sudden you drop a car on it, or not drop it, there's no impact, like you just all of a sudden the car appears, then the maximum dynamic factor would be 2. Because as long as everything is linear too, we're assuming that the stiffness is linear. Now,
Just curious, when you model dynamic analysis and abacus, let's say,
you can ask me next
sure.
on Monday.
Oh, I'm not.
Sure, go ahead, sorry. Yeah.
Will it allow you to model a resonance?
Yeah, well, you can model anything. So resonance. Well, I mean, it depends because so we'll take 5 minutes and I can answer this question.
Sorry.